All right, today we're going to play detective. We're on a mission to uncover the fundamental clues that split all the elements we know into two huge families. You've got your metals and your nonmetals. So what actually makes a metal a metal? Let's dig in and find out.
So let's get right into this elemental mystery. And it really all kicks off with a pretty simple question about stuff we see all the time. I mean, on the surface, they seem like they're from different planets, but the reasons why, well, that goes all the way down to the atomic level.
You know, on the surface, it looks pretty straightforward. We have metals over here, things like iron, gold, and nonmetals over there, like carbon and oxygen. But this is just scratching the surface. The real story, the one that explains everything, is hidden in their properties.
Okay, first things first. Like any good detective, we start by gathering evidence, using just our senses. We're going to look at the most obvious physical clues that help us tell these two families apart. The very first clue is one you just can't miss, that shine. If you take a piece of metal and give its surface a quick clean, you see this brilliant, unmistakable gleam. That property is called metallic luster, and it's a classic signature of a metal in its pure state. Next up, let's see how they handle a little pressure. If you hit a metal with a hammer, it doesn't just shatter into a million pieces, it bends, it flattens out. This ability to be hammered into thin sheets is called malleability, and it's what makes metals so incredibly useful for everything from cars to jewelry. And this is where it gets crazy. Some metals take this property to a whole other level. Gold and silver aren't just kind of malleable, they are the most malleable metals we know of. You can hammer them into foil so incredibly thin they're almost see-through. Here's another key piece of evidence: ductility. This is the amazing property that lets us stretch and pull metals into thin, unbroken wires. Honestly, without ductility, our entire modern world of electricity and electronics just wouldn't work.
And if you need a number to wrap your head around that, get this. A single gram of gold, which is the most ductile metal, can be drawn out into a wire that's about 2 kilometers long. That is just mind-blowing. And the list of physical clues just keeps growing. Metals are fantastic at conducting heat and electricity. That's why your cooking pots and electrical cords work so well. They also tend to have really high melting points, and they're sonorous. That means they make that classic, clear, ringing sound when you strike them, kind of like a bell. Now, physical clues are great, but they're not the whole story. Sometimes they have exceptions. To really, truly crack this case, we have to dig deeper. We have to uncover a motive. And to do that, we need to look at their chemical behavior, their unique elemental personalities. This is where it gets really interesting. Because, see, while physical traits can sometimes fool you, like graphite, a form of carbon, which can conduct electricity, chemical properties, they don't lie. They give us a much clearer, much more definite way to classify any element. To really get them, you have to see how they react. So how do we do that? Well, we put them to the test, systematically. We see how different metals react with common things like the oxygen in the air, with water, and with simple acids. And when we do this, a really clear pattern starts to emerge. It lets us create a kind of power ranking, from the most reactive down to the least. And this is what you get, the Reactivity series. This is our master list, our lineup of suspects. Up at the top, you've got the really aggressive characters like potassium, which react like crazy. Then, as you go down the list, things get calmer and calmer, all the way to gold at the very bottom, which pretty much minds its own business and barely reacts with anything. So what's driving all this? What's the motive behind all this reactivity? It all comes down to an atom's deep-seated need to feel stable, which means having a full outer shell of electrons. Metals, they have a few extra electrons they're happy to give away. Nonmetals, on the other hand, are looking to grab some. This whole atomic give-and-take is the very essence of their chemical identity. Now, knowing these chemical personalities isn't just for a pop quiz. It is the key that unlocks our planet's resources. It's how we pull off the greatest heist in history, taking pure, useful metals right out of the rocks in the ground. You see, metals are scattered all over the Earth's crust, locked inside minerals. But we're really interested in something called ores. An ore is a special kind of mineral that has such a high concentration of a metal that it actually makes sense economically to dig it up and go through the trouble of extracting it. For a lot of the common metals, the ones right in the middle of that reactivity series, the extraction is a classic three-step job. First, you convert the ore into a metal oxide. Step 2, you use something else, often carbon, to basically steal the oxygen away, leaving the metal behind. And finally, step 3, you purify it to get the really good stuff.
And some of these chemical reactions are just wow. They're incredibly powerful. Take the thermit reaction. It's so intense that it unleashes enough heat to create molten iron right on the spot. It's perfect for something like welding massive railway tracks together out in the middle of nowhere.
Okay, so we've gone to all this trouble to get the pure metal. But now we face our final challenge. We have to protect it from its own reactive nature. We need a cover-up to stop it from decaying and turning back into a compound.
And you've definitely seen this problem before. It's called corrosion. You expose metals to air and moisture, and they just start reacting with their environment. Silver gets that black tarnish, copper develops that famous green coating, and of course iron, well, iron creates those flaky brown bits we all hate called rust.
The good news is we've got a whole toolkit to fight back. We can put up a simple barrier with paint or grease, we can get clever and apply a sacrificial coating, like the zinc used in galvanizing, or we can use even more advanced methods to change the metal surface and properties entirely.
And that leads us to maybe the cleverest solution of all, alloying. This isn't just mixing stuff together. This is like molecular engineering. Take pure iron. It's actually pretty soft, but you mix in just a tiny bit of carbon and you mess up its neat crystal structure. The result? Steel, a material that's way stronger, harder, and much better at resisting rust.
So this brings us to an incredible final thought. Understanding all these elemental rules doesn't just help us explain the world we have. It basically hands us the blueprint to design a new one. We can now stop asking what is this material and start asking what do we want this material to be. The future of materials, well, that's up to us to create.